So just a few comments up front. First of all, thanks much for inviting me here for this wonderful meetup. I think this is really an exciting time for quantum technology. And I think the speakers that we've had here really kind of exemplify everything that's going on in quantum computing with neutral atoms, starting from the far end of the science side of things. The last speaker, Brian Lester at Atom Computing, talking about new technology for quantum atoms, for quantum computing with atoms as well. I think if I have anything to add to this, and I guess I'll just kind of put this up front, is that if quantum computing with neutral atoms is really taking off, what we need is an ecosystem of companies and academia working together to achieve those aims. And so I do think that that ecosystem is starting to come out, and what QuEra Computing would like to offer to that kind of ecosystem is actually kind of a new thing in tonight's presentation, and that's quantum computing services, which is to be able not only to produce this hardware, scale it to competitive sizes where we might be able to see things like quantum supremacy and quantum advantage on neutral atom quantum computer, but also to make these systems available to the masses as well. Take them out of the university research labs and put them into people's hands. So actually the quantum computers that we're building at QuEra Computing, we're a new startup here in the Boston area. I think I represent the youngest institution here tonight. I don't think that I'm the youngest speaker. I think Brian probably has that honor. But just to kind of put a bookend on something that Nir said at the beginning here, neutral atom technology really kind of kicked off with the advent of laser cooling, and Nir mentioned Steve Chu. Steve Chu was actually my graduate advisor. I have the distinction of being, I think, the second to last graduate student out of Steve Chu's atomic physics group. So it's really, kind of fulfilling to see that technology really lead to the next chapter in quantum control and quantum computing. So the systems that we're looking at QuEra Computing and trying to put online over this next year, really, I'm trying to show everything on a single slide here up front at the beginning. And if you look down at the bottom of the screen there, you can see what this technology is built on. And by now you've seen a lot of images like this, but every one of these dots in the images below is a single atom held in an optical tweezer. So this is a focused laser beam, a dipole trap, which holds the atoms, and we cool those atoms down very close to the motional ground state inside of that trap. So we're talking about microkelvin temperatures. That's 1/1,000,000 of a degree Celsius above absolute zero. And inside of that laser trap, we're actually trying to impart information to the atoms and drive them into entangled states and do all the basic things that you want to do for quantum computing. So there are two different ways that we can do that with the rubidium-87 atoms that we work with at QuEra Computing this year. One way that we can do that is to shine focused laser light onto the atoms and flip them between internal states in their hyperfine ground state manifold. And what that allows us to do is have very long-lived coherence times and store quantum information for a while. Now, of course, the magic in quantum computing actually comes from entangling operations. So the other thing that we can do, and you've seen this in various talks already tonight, is drive them up into very high-lying, high excited states called Rydberg states. And in these Rydberg states, the atoms obviously have long-range interactions through dipole-dipole type interactions. Now, one of the really wonderful things that we can do with neutral atoms, which is maybe a little bit distinct from other systems, is not only can we do many simultaneous single qubit gates, but we can also do very efficient kinds of entangling operations. So not just shining light on two of these atoms in the array at once and putting them up into the Rydberg state, but actually driving many of them simultaneously up into the Rydberg state. And you've seen some examples of that in Antoine's talk previously. And so I'll show you some examples of how we can actually use these kind of quantum systems to attack problems which, they're named problems in computer science. Antoine actually gave you a little bit of a sense of this when he brought up the maximum independent set problem. And I'll tell you about how at QuEra Computing, we're actually moving to try to put those kind of systems up online and let people actually do those kinds of calculations for themselves using our machines through remote cloud access. Okay, so I do want to point out that I am on a truly fantastic team of founders who started this company. I am the youngest of this group, and I have to say I'm the least accomplished of this group. I'm really privileged to be on a team of some of the kind of luminaries in the field of computing with cold atoms in the form of Misha Lukin and also Marcus Greiner, both professors at Harvard University. as well as Vladan Vuletich and Dirk Englund at MIT. Now, between this team, we actually have quite a bit of experience on not just quantum simulation with neutral atoms, but also a fair number of other kinds of quantum control and quantum communications platforms. In fact, between us, we've covered not just neutral atoms, but also ions, and nitrogen vacancy centers in both Misha Lukin's group as well as Dirk Englund's group as well. So you would think that with a group like that, starting a company, we might pursue a range of different kinds of quantum computing technologies, but that's actually not the case. We've decided to focus on just one, and it's been the subject of all of tonight's talks, which is neutral atoms. And the reason that we've chosen this is that we really believe that this is the most scalable platform to date for quantum computation. We think over the next several years that this really will be kind of the leading edge technology for performing quantum computations. So just to give you a quick outline of what I'll talk about tonight, I've told you a little bit about how our platform actually works and the team behind QuEra's founding. I'm going to start off with just a little bit of a history about how the company was founded, where we're headed, and how we're starting to get things off the ground. And then I'll go into some of the early Harvard and MIT results that led to the founding of the company, and try to give you a sense of excitement about how quickly things are moving by showing you some of the recent results that have come out of the Harvard and MIT labs just over the last several months. Once I've done that, then I'll tell you in detail a little bit about the commercial quantum computing engines that we're developing on site at QuEra, and how we're trying to bend those towards real commercial quantum computing that hopefully at some point demonstrates, kind of a threshold, which is the first time that a quantum computer is actually useful to do something. And so what we're aiming for there is to look for the first cases where one might expect to find some kind of quantum advantage in doing a calculation which is actually useful for people. And then finally, what I'd like to do is tell you a little bit about how we can take these cold atom systems and really improve their programmability, which is something that Emmanuel Bloch mentioned in the very first talk of the evening. And we think that this is really one of the most important corners that we have to turn with neutral atom technology. And so I'll give you a sense of how exactly it is that we're building new kinds of photonic systems that allow us to really increase the scale of individually addressed systems of cold atoms, and how we can make those universally programmable as well. So as I mentioned, QuEra, the company, is actually an outgrowth of research which was done over the years 2016 to 2018 at Harvard and MIT. And these were really kind of breakthrough experiments done with the neutral atoms, really looking at quantum simulation and computation. But it was work really not just out of the people that I showed you before that founded QuEra Computing, but also a very large contingent of really talented young scientists. And so I put their names here. I've given you a little bit of a picture. This picture was taken just as background just before the pandemic had broken out. Basically, it was on its way to the US. So this Harvard team ran into the laboratory and very quickly turned their quantum computer with neutral atoms into something that was remotely accessible so that they could go home, sit in their apartments without infecting each other and actually run this machine. And a lot of the data that I'll be showing you today from their efforts was actually taken from their living rooms. So that research continues, and what I would say is that that university research really gives us an opportunity to really do discovery-driven quantum research. And I think this is an important point and goes back to this idea of an ecosystem between both academia and business as well. There is quite a bit of discovery left to be done with these cold atom systems or quantum computing in general, really before we get to the point where these things are useful. Now, our mission at the company is actually to develop cutting-edge commercial quantum computing hardware and services. And so what we're doing is working very closely with these university research groups to understand what they're doing and translate it as quickly as possible as we can into meaningful cloud-accessible platforms for people to actually get their fingers dirty, trying out quantum systems and designing quantum algorithms and things like that. So we founded QuEra in 2019, about middle of 2019, with a little bit of seed funding. We went out, we hired some of these quantum engineers that we're hearing about, senior research scientists and so forth at QuEra. And just at the beginning of this year, we moved into a 10,000 square foot facility that we are now trying to turn into a quantum data center, where we're actually building up these machines and bringing them online. Now, I should point out that that was also just about the time that the pandemic was breaking out. And so this 10,000 square feet turned out to be really useful. It also turned out to be really useful that that quantum data center that we leased out actually was a giant vacant building. We were the only tenant inside of this building. So it's allowed us to be able to spread out and continue our research and development inside that quantum data center in a safe way. So through 2020, we also obtained some grant funding and things like that that also allow us to really make a lot of headway on this work. But I think most important to point out is that just at the end of this year, we've now really finished building our first commercial quantum computing system. So we've been able to do that in record time despite this pandemic that's been breaking out. So I'm going to just go back a few years to 2016 or so. And I'm going to tell you about the experiments that were being done at Harvard and MIT that really convinced me that now was the time to come outside of my research laboratory at the time, go into the commercial world and start pushing these systems for actual commercial deployment. And so these are experiments that were done in Misha Lukin's group around the time of 2016. And these kind of give just a basic idea of how to build a quantum computer out of cold atoms in a very simplistic way. So what this group did is actually just produce a series of optical dipole traps or optical tweezers along a line and essentially load atoms into those optical dipole traps randomly, non-deterministically, using methods in laser cooling. And then to look at those randomly loaded traps in real time, identify where atoms were at and where they were missing, rearrange them using the kinds of things that Brian was just talking about in the last talk, acousto-optic deflectors, to rearrange and actually produce an entropy-free array where we've actually regularly loaded exactly the type of array that we want to. After doing that, we can actually compute in the same ways that Antoine was talking about by shining light on these atoms, which drives them resonantly up into highly excited Rydberg states. We do the same thing that Antoine was talking about. We use 1013 nanometer and 420 nanometer light to address the same kind of intermediate state in between the Rydberg state and the ground state, but that allows us to very quickly put the atoms up into that excited state where they interact. Now, the reason that this convinced me, and I think others, that neutral atom technology was really ready to take off, is that from this very basic starting point, which is a relatively simple cold atom machine to build, compared to the state of the art of things that, for instance, are going on in Emmanuel's group right now with quantum simulation, is that we could use this simple machine basically to do kind of the etudes in quantum computing, which is to explore all of the necessary ingredients that have to really go into any platform that would be successful at quantum computing at scale. And so what Harvard and MIT did as a team was really look in two different kind of camps of experiments to kind of bear out the principle that this is a platform that could really take off. They looked at quantum computing and simulation kind of in the NISQ era kind of style of looking at things. NISQ stands for noisy intermediate scale quantum devices. And there they were able to show some very interesting experiments in quantum many-body dynamics. I'm going to show you an example of one that was done just recently with a slightly more complicated apparatus. But also on the theory side of things, they were able to show that we could actually look at computer science problems like network analysis problems and find ways of actually using cold atoms to realize computer science style kinds of calculations. So not just finding the ground state of a quantum system using quantum simulation, but to actually do a calculation of some sort. And beyond that, to do other things as well with algorithms, looking at things like machine learning based off of quantum machines. Now, at the same time, we also want to show kind of sustained progress towards that dream that has always been there of doing quantum computing in a very kind of gate-based way or in a digital way, as Emmanuel was referring to before. So on that score as well, the Harvard MIT team took the kind of single platform and showed a few things that were really important along those lines, not just being able to assemble defect-free qubit arrays, but also being able to produce very high fidelity neutral atom quantum gates. And I'll show you some of the targets that QuEra Computing is looking to achieve based off of that work in the near future. But not just that, also being able to really assemble very large macroscopic superposition states, so Schrodinger cat states of qubit numbers that are on the scale of 20 or so atoms. So just to give you a sense where that kind of research has reached, and you've seen some similar results out of Antoine's laboratory previously tonight, but I'll just give you a sense of how these experiments have evolved and what we're able to do now. Those experiments that I just showed you were done between 2016 and 2018. Flash forward to just this last year, 2020, and this group is now working in 2 dimensions. And the way that that's done is actually shown on the left there. You can see how we make arrays of 2-dimensional traps, optical dipole traps to trap the atoms in, using spatial light modulators. So this is very similar to the kinds of things that Brian was talking about before, as well as Anton. And the way that we do this is actually to use a liquid crystal on silicon modulator, and we bounce the light off of that, form a hologram that allows us to produce any kind of system of traps that we like. Now, in this particular study that I'm showing here, which is now on the archive and you can look up, different kinds of basically regular geometries of optical dipole traps were used. And what you can see in illustration B here is a scattershot loading of a rectangular array, randomly loaded with atoms, which in real time, this group took a picture and within 10 milliseconds used a crossed AOD, like you heard from Brian Lester in the last talk, to pick up atoms where they were missing and put them where they belonged in order to produce an entropy-free 2-dimensional grid of atoms where every grid site is occupied with an atom with certainty. From that starting point, then we can turn on Rydberg excitation light and actually let the atoms transition into the excited state. Now there's a wonderful effect due to these very long-range Rydberg interactions between the atoms called the blockade effect, which prevents any 2 atoms which are close enough together, basically within a Rydberg range of each other, and Antoine described this previously, from transitioning into that excited state at the same time. And so what that means is that very similar to antiferromagnetic states in quantum systems, we have a situation where in this regular lattice, if we adjust that Rydberg range to be between the nearest neighbor and next nearest neighbor's facings, then we can actually produce a kind of antiferromagnetic state on that lattice. Now this is a particular example of a bipartite lattice. So obviously there are 2 sublattices there that are kind of interpenetrating. And what you're seeing is the ground state of atoms basically occupied or unoccupied on one of those 2 sublattices. Obviously there are 2 degenerate states there as well, and we'll come back to that in just a minute. Now, obviously, we can also make other lattice geometries, and so in C and D, you're seeing those other kinds of lattice geometries and the antiferromagnetic states that we can produce on those. So these are pretty big systems. These are 15 by 15 arrays, so this is 255, 256 atoms put into these arrays. And so these are some of the largest quantum systems that we can keep quantum coherent over long time frames. Now, once you have a system like that, you can actually start to do many-body physics in a very meaningful way. And so what Harvard and MIT have actually done now is basically taken that Rydberg radius as a tool, as a parameter, as well as the detuning of a frequency sweep to put those atoms into the ground state. And with those 2 parameters, kind of map out the quantum phase diagram of that system. And so just like Antoine was talking about, we can analyze those images after readout, extract order parameters for different types of phases. And what you're seeing on the right there are 3 different types of phases and 3 different order parameter measurements that were actually measured in the laboratory by basically just kind of correlating where we see atoms and where we don't in the images that are taken after the transition. And so actually, if you try to model that with numerics, you can see the results on the bottom there. That's DMRG calculations that are done to try to figure out what that ground state should look like theoretically. One thing that I'd like to point out is that we actually can't simulate this system with DMRG at the scale that we actually ran the experiment. So these are smaller scale classical simulations that are shown at the bottom. So you can see very good agreement, but actually we're already running quantum computers at a scale that we can't actually simulate. So in a certain sense, you might think of this as kind of past the point of quantum supremacy. Now, actually, we can do even more exotic types of measurements. We can also look at the dynamics of these types of systems. And so this is a very fascinating experiment that was done just the last couple of months. I mentioned before that in bipartite lattices, we actually have two ground states. What we can do is prepare one of those ground states adiabatically and then very suddenly change the parameters of the system. When we do that, then what we can see is for very short evolution times, the quantum system just goes off into a wild superposition of many different kinds of quantum states. But if you wait just a little bit longer, you'll see actually a transition from the ground state on one of those sublattices on the bipartite lattice onto the other. And if you wait yet longer, you can actually see it revive, which is to say it goes through that transition, comes all the way back to the initial starting point. And if you keep letting it do that, it actually will oscillate through those states for many iterations. Now, there are very interesting things going on here that I think nobody really has the capacity to fully predict at this point. But we can actually drive these systems even periodically, not just with quenches, but actually change these ground state governing parameters periodically in time. And when we do that, we see all kinds of interesting effects, like a locking of the frequency of oscillation between these states to the drive frequency, and also an extension of the coherence times by factors of up to 5 already. So these are very interesting quantum dynamical systems, and it really illustrates the kind of scale at which these quantum simulators can already operate in the laboratories now. So these are very fascinating experiments, but at QuEra Computing, our mission is actually to take these things and really produce a general purpose tool that's open for access and that people can use more broadly. So what we're looking to do is really to quantum compute in a two-step process, assemble memory banks of cold atoms to store information in the kinds of ways that you've seen before, dynamically moving atoms around, producing defect-free arrays and such. And then in the second step, really start to program these things, program in quantum computations, doing things like in gate-based models like we've always envisioned to do. And so we at QuEra are basically trying to assemble these kinds of systems now and bring them online. So obviously, it's very important also that these systems be very quantum coherent. So you've heard these kinds of numbers in previous talks, but we're aiming to bring on online computers that have gate speeds kind of at the 4 to 10 megahertz scale, but also importantly with very high fidelity operations. And so the machine that we're bringing online right now is expected to operate at 99% fidelities, although we haven't had a chance to measure those yet. But we also are committed to increase those fidelities over the next 30 years to 3 nines, 99.9% fidelity. So just to give you a sense of what it takes, to start a startup like this and actually start to produce commercial quantum computing engines, I'll just give you kind of a brief kind of tour of our last year here. So in about March, and I guess Ryan showed some pictures like this just previously. In March, we started in this big vacant building in Boston, moved in and built basically an atomic physics laboratory in this vacant building. And by July already, we had really trapped our first cold atoms and formed our first magneto-optical trap. So that was with a team of initially about 4 people that grew to 7 through the year. And you're seeing those 7 people up at the top. They're all masked up, working on the apparatus, trying to stay socially distanced. But clearly, while we took that picture, we seem to have failed a little bit. But by October, with that team, we had basically all of the pieces in place for a functional build of a quantum computer. And so this was really a tour de force, people working in shifts, trying to avoid each other, avoiding contacting the same surfaces, the kinds of things that only 2020 could bring, only 2020 and the coincidence of starting a startup at the same time. But I am very proud to announce that just within the last month or so, we had brought that machine online, and we are now at the point of imaging single atoms. In the lower right, you're seeing a picture there, which is the very first day that we trapped single atoms. Within minutes of that happening, and you're seeing one of the first pictures of the actual first 4 atoms that we've trapped in optical tweezers and imaged in that system. So just to highlight, the quality of the team that's been able to do this. When we set out to do this, I wasn't really sure that we could do it in the time frame that we were talking about. That was before the pandemic broke out. So I really want to highlight this team of scientists that's been able to pull this off. And I thought since that last image that I put up had all masked people that I would actually give you individual pictures without the masks and with some smiles on their faces. And I just want to point out that the really strong team of scientists, to a large extent pulled out of laboratories at the Center for Ultra-Cold Atoms at Harvard and MIT, but also now the team is growing beyond that as well. And we've added a few more people since this team put this machine together over the last year. So I think, I should give you some sense of scale for how we expect these machines to perform. And we're basically validating these design builds as we speak now. But we've built these machines really to work in two different kinds of modalities. One modality is to use global addressing. So basically, in the kind of modality that I showed you before with the Harvard and MIT experiments, where we light up arrays of atoms with atoms positioned kind of in arbitrary positions in a plane at the scale of something like 256 qubits and scaling higher to 512 qubits next year. But we're also looking to make these machines a little bit more programmable. And to do that, we actually have to focus individual laser beams onto each of those qubits and manipulate them singly. We're aiming to do that this year at the qubit scale, about 64 qubits, and also to be able to encode not just in Rydberg basis light, but also with hyperfine changing transitions as well. So we're aiming in these cases to have native gate sets that include not just single qubit gates, but also multi-qubit collective gates. So things like Toffoli gates and CNOT gates, but generalized to K qubits, where K is not just 2, but larger than that. Now, I should point out that neutral atom systems actually have reasonably high connectivity. So these are fully connected systems over reasonably long range. So I've shown you results already with very high fidelities that actually work over nearest neighbor and next nearest neighbor in relatively tightly packed kind of optical tweezer arrays. So we expect to be able to continue that with the machines that we're designing at QuEra. Obviously, one of the strengths of the Rydberg platform is that our gate speeds can be quite high. And so we envision working at 10 megahertz or so for individual gate speeds as well. Now, I mentioned before, single qubit and multi-qubit gate fidelities are very important to us. So we're targeting to have 99% fidelities with the machine that we built this year. Now, these are machines that we really have built from the ground up for cloud access computing. We had committed to that before this pandemic broke out this year, but now we see the advantage of that in multiple different ways. Running these machines from afar is not easy to do. You're seeing pictures of these machines up at the top of this slide. Obviously, these are still the kinds of research devices that you see in university laboratories with lots of mirror mounts and things like that. It takes quite a bit of effort to be able to actually run these machines without physical contact, but we've designed our machines to do that from the beginning. We're also aiming to have very high reliability and uptime. And so this machine, we're hoping to hit kind of 80% numbers of uptime. Now, I think this is really important to underscore, and since it hasn't been said here today so far, I think I'm going to kind of emphasize this, but if your mission is really to bring quantum computing systems to the masses and to expose their utility to people who are, say, not themselves PhD physicists or not themselves atomic physicists, one of the hardest problems that you have to attack is really how to not just build a machine, but then make it useful for people when they access it from afar through the cloud. And so we have hired at QuEra a whole team of software developers essentially to work on the top end of this stack, which is really not just to coordinate the hardware that has to talk to each other in order to make these machines work, but also to provide the software tools, things like compilers and things like optimizers, things like servers, and then very importantly, programming interfaces that allow people to really understand what they're doing and intuit how to be successful in utilizing quantum machines in different ways. So this is a work in progress, but I think that we will have our first version of a quantum stack that really looks like what you see pictured here as a proof of concept sometime during this next year. Most of those pieces are actually already in play. And I think it's really important also that we be able to take these machines and task them on problems that really make sense as computing engines to the world. I think quantum simulators are great, and neutral atoms are really great at quantum simulating things in scale. But that issue of really programmability is super important. And I thought it would be nice in this talk today just to give you a sense of how we can kind of turn the corner and start with something that really, kind of looks like quantum simulation, but at the same time looks like it's solving computer science problems as well, by describing one of the targets that we have at QuEra for doing real world computations kind of as soon as possible. And Antoine alluded to this previously. Maybe I'll just give it a little bit more character here. What we're looking to do is actually attack a problem in network analysis, which is known as the maximum independent set problem. And the reason that this one is so important to us is that this is an NP-complete problem in classical computer science, but it's also one that requires essentially no encoding overhead for Rydberg atoms. So we really like this problem as kind of a demonstration and maybe actually a first shot at looking for something that has quantum advantage in it. And so what this problem actually does is it takes a network graph like you're seeing on this slide here, consisting of vertices and edges connecting those vertices. And it looks for the largest set of vertices in that graph, no two of which are neighbors, no two of which are joined by an edge in that network graph. And so you can kind of see why it is that Rydberg atoms can very efficiently attack this problem. Because if you study the right type of graph, say one where the vertices correspond to positions in the two-dimensional plane, and they're connected by an edge in that graph only if they're within a Rydberg range of each other, then you can see very quickly that this problem is basically the same as finding the antiferromagnetic state on an arbitrary graph. And so the kinds of things that I was showing you before from the Harvard and MIT research, well, those are very germane to this type of problem. Now, it actually turns out that if you take a classical computer cluster and you task it on that problem at the scale of about 500 nodes, there are actually instances of that problem, that network analysis problem, that no one has ever actually even found the answer for what the maximum independent set of that particular graph is. If you go up to about the 300 node level, that's the type of problem that you can tune up a high performance computing cluster for something like 24 hours to try to find the answer. So we like this problem at QuEra for all of those reasons, but we also like it for another reason, which is to say that this problem is also industrially relevant. For example, if you associate with each of those nodes in that graph a wireless transmitter, and associate with the Rydberg range, the transmitter's range, what you're describing is an ad hoc wireless network of radios. And if you want to calculate the most efficient way to pass a message through a network like that, which is a real world problem, actually the way to do that is to first calculate the maximum independent set of that graph and then use it to compute the message passing backbone. So this is something that comes up in the Internet of Things. It's also something that comes up in 5G wireless. It's a very basic bottleneck, especially in radio networks that are evolving in time. So for instance, if all of those transmitters are sitting in your cell phone in your pocket, obviously this thing moves very quickly. So being able to compute those things in real time is very important. Yeah.
We are running out of time. Can you try to wrap up soon?
Yeah, so I'll just skip over this part. Basically, all I wanted to say is that there are 4 things that we like about this problem. It's hard on classical computers. We know that we can solve it with quantum computers, especially hybrid quantum computers. We know that the resources are small, and finally, we know that it's useful. So this is a problem that we love. So QuEra has basically taken all of the first steps to produce a software stack to be able to attack these problems. High performance quantum emulators that are specific to the Rydberg platform, stochastic optimizers that allow us to do those hybrid quantum computing steps. But we're also in our algorithms and software team pursuing different types of gate designs that allow us to use limited resources in a quantum computer to try to be able to do universal gate-based quantum computer also in this platform. So just as a last parting message, I do want to say that there are technical hurdles still left in this platform. And so we also are trying to attack head-on some of those scaling problems. And one of the primary problems that we have to address is how to produce highly scalable systems where each of the qubits is individually addressable. So we are also at QuEra designing integrated photonic circuits, particularly in silicon nitride, to try to scale up the amount of control that we have on the qubits. And so here you're seeing one example of that where we're actually integrating waveguides on chips with modulators and trying to address qubits at scale. So I guess with that, I'll just kind of say thanks, put up one last slide that just shows you kind of the timeline that we're looking at over the next year or so to not just finish up this first quantum computer that we've basically putting up online over the next year, but also the machines that we expect to be building in the next year. So thank you very much.
Okay, thank you very much.